Hi, everyone. I'm really glad to be here. And today I'll be talking about our work on surveillance, privacy, and social control. And this is joint work with Grace Bogosian and Seni Kamara at Brown University. So to set some context, there's been this long-running debate around surveillance. So on one side, we have governments and government agencies who claim that some amount of surveillance is necessary for national security and law and order. And if you have nothing to hide, then why should you as a citizen be afraid of government surveillance? So that's like one side of the debate. The other side are individuals and civil rights groups, which are concerned about privacy of data and devices, and also some fear that surveillance will lead to a surveillance state with sort of a big brother situation in an Orwellian future. So this has been a long-running debate, and there's not really one right answer to this. So what is this talk about? This is a complex issue. So it touches upon law, ethics, philosophy, sociology, and more. And what we are here to say is that at least some part of this is an algorithmic problem. And what do I mean by that? Surveillance, when stated in an algorithmic sense, is essentially the problem of finding bad actors in a society efficiently. And I've put bad in quotes because it's however the government chooses to define bad. And the notion of efficiency is also not the normal notion of efficiency for an algorithm, but I'll come to that in a bit. So what are our contributions? We'd like to add a CS perspective to an aspect of this debate. And what we'd like to introduce in this talk is a framework to study surveillance in networks. And inside this framework, I'll be talking about the loss of privacy as well as social control. And again, I repeat, this is not the complete perspective. We don't claim to solve the problem with this. We are only trying to add a new way to look at it in the hope that it'll give us some understanding of this aspect of the problem. And this is a work in progress, so we welcome feedback and comments or anything the audience would like to tell us about this work. So the outline of the talk will broadly be I'll introduce our framework, I'll talk about the two applications, I'll talk about privacy costs, and then I'll talk about social control, and I'll conclude with some questions for future work. So when we talk about society, and we talk about individuals in society, and we talk about modeling algorithms in society, we think of a graph or a social graph, which is represented by V, E, and chi, where V is the vertices of this graph, and each vertex corresponds to a person. So you think of each little vertex in this graph as being one person. And E, or the set of edges in this graph, which connect the vertices, represent interactions between these individuals. And for now, we're not committing to any type of interaction. So this could be an electronic communication. It could be an in-person interaction. For now, we're just saying this is a social network of some kind. And these edges are interactions and these are people. So what is chi? Chi is, we define chi to be a coloring function. And this coloring function defines attributes on the vertices. So it takes as input a vertex and it outputs an attribute or a color. And this function could be arbitrarily complex, but for now, for the purpose of this talk, let's assume this function is binary and that it outputs a color on these vertices. And the color is either green or red. And the red vertices are the bad actors in society. Now, this is clearly an oversimplification, but again, this is for the purpose of this talk. And so chi takes as input one vertex of this graph, and it outputs the color or the attribute of that vertex. So chi of this vertex over here would return green. And there are many different ways of coloring this graph. There are many possible attributes inside a social graph. So given this setup, we can now reformulate the surveillance question. So now the surveillance question is, how does the government go about finding these red vertices in the graph efficiently? And then there's a question of what does efficiency mean, and we'll come to that in a little bit. So what are the allowed operations on this graph? So this is our ground graph, and there are some surveillance operations that are allowed in our framework. And we call these operations eavesdropping and targeting. And I'll explain them over the next few slides. So eavesdropping operations, and I have the ground truth graph over in the corner here. I hope all of you can see my cursor because I'm going to be pointing at things a bit on this slide. So we're given this graph and it's blank. And for now, we're assuming that the surveillance knows nothing about this graph. And an eavesdropping operation is performed on an edge, or it's performed on an interaction between two vertices. So let's look at this edge here. So this edge UV, and over in the ground truth, we can see that this edge connects a green vertex to a red one. And what if there was an eavesdropping operation on this edge? What would we expect this operation to output? So we claim that in this interaction between a red and a green vertex, the red vertex does not express its redness. Or in some sense, if you eavesdropped on this interaction between a red and a green vertex, what the operation would end up revealing is the interaction of two green vertices. And this leads us to sort of define the notion of the color of a vertex contingent on who the vertex is talking to. So this is contingent color, or chi bar. So you can see here that the vertex V's contingent color with respect to the vertex U is green. And whenever a green vertex is talking to a red one, the red one always shows up as green in that particular interaction. So that's the notion of a contingent color. And if you look at this function, that's all this function is expressing. It's essentially saying that if a red vertex talks to a green one, it's going to show up as green in that interaction. And a green vertex always shows up as green in every interaction. So again, if we look at this edge over here, UV, we'll see the same output. The operation would take in this edge and output and would reveal an interaction between two green vertices. However, this edge over here in this graph is an edge between two red vertices. And presumably this interaction will reveal something about the nature of those two vertices, reveal something about the redness of those two vertices. And so the eavesdropping operation would output two red vertices. And now we can formalize this notion of an eavesdropping operation on an edge, where eavesdrop takes as input an edge, UV, and it returns this contingent color of U with respect to V, and the contingent color of V with respect to U. So that's the first type of operation on this graph, and it happens on an edge. The second category of operations that we have is called a targeting operations. And if you could think of eavesdropping operations as sort of the government intercepting your messages, you can think of targeting operations as more invasive surveillance. So imagine one individual being tailed, potentially having their devices broken into, and all of their data examined. So this is the symmetric thing. It's performed on a vertex, so on an individual. And what do we expect targeted surveillance to reveal? So let's look at this vertex V. And we can imagine that a certain invasiveness, like because of how invasive the surveillance is, it reveals the true color of the vertex. And so we would find out that the operation would discover that this vertex is red. However, because of the pervasiveness of this particular type of surveillance, it would also uncover some information about the vertices which are interacting with this vertex. So not only does this operation uncover the true color of the vertex V, it also uncovers the contingent colors of the neighboring vertices. So if the vertex V were to be targeted in a surveillance operation, the operation would reveal that this vertex is red, and it would reveal that the contingent colors of both neighbors were green. Now let's look at one more example. And this vertex is green. And the true color of this vertex is green, which would be revealed by the targeted operation. And the contingent colors of all the neighbors also appear green because that is the nature of this vertex. So even though these two vertices are truly red, in interactions with this vertex, they appear green. So then we define the target operation on a vertex V to return the true color, chi of V, and the contingent color, chi bar, for any U that's a neighbor of V. So all these circled vertices here are the neighbors of V in this graph, and their contingent colors are being revealed by the target operation. So those are the two operations that we allow on the graph. And now we can define the notion of a surveillance algorithm. So what does a surveillance algorithm do? It takes as input this plain graph and output and queries eavesdrop and target, and outputs a set of red vertices in this graph. So we define what is the function of the surveillance algorithm. It has to find all the red vertices in the graph. So we define this notion of correctness, which says let the surveillance algorithm make QE queries to eavesdrop and QT queries to target, and it outputs all the red vertices with probability at least 1 minus epsilon, in which case we call this algorithm QE QT epsilon correct. Now, there are many different ways to define correctness. You could say maybe algorithm doesn't need to find all the red vertices. Maybe it only needs to find a significant fraction of them. So this definition could be tailored to the application. And you could think of all sorts of different types of algorithms on this graph. Okay, so now that we've talked about what an algorithm does, we can go back to the question of what does efficiency mean? And what are the costs of surveillance? So there is an obvious operational cost. So to surveil an individual, potentially the government needs to buy hardware, software, hire people. So there's like manpower cost as well as computational cost. And these costs, we call them surveillance cost. And we denote them as CE for an eavesdrop operation and CV for a target operation. However, each operation in this graph also has a privacy cost. And this is what we're interested in our frameworks to understand the privacy cost better. How do we define the privacy cost? So intuitively, if we look at this graph, what is privacy? Privacy is lost when you have to surveil an innocent person to find someone who is a bad actor. So if a surveillance operation touches a green vertex in this graph, that would be considered as a privacy cost of that operation. So the number of green vertices surveilled during an operation is the privacy cost of that operation. And similarly, if we were to look at, say, this edge over here, and suppose this edge were to be eavesdropped on, the privacy cost of that eavesdropping operation would be 1, because one green vertex is being touched by this operation, or one green vertex is being surveilled. Similarly, if we were to look at the targeting operation of this red vertex, again, one green vertex is being surveilled. So that would also, the cost of that operation would be 1. However, if the red vertex down here were to be surveilled, it has 2 green neighbors. So the privacy cost of that operation would be 2. Okay, so now what is the privacy cost of an algorithm? The privacy cost of a surveillance algorithm that makes QE queries to eavesdrop and QT queries to target is the total privacy cost of all the operations conducted by this algorithm, or the total number of green vertices that will have to be touched by this algorithm or have to be surveilled by this algorithm. And again, like I said before, there could be many different types of algorithms. So you could think of an algorithm that samples a bunch of vertices till it finds a certain number of red vertices. You could think of an algorithm that samples a bunch of edges. And these are all different things that could be applicable in different settings. However, what are we interested in? We're interested in knowing what is optimal for privacy, or what is the lower bound, what is the least privacy that will be compromised by a surveillance algorithm. So let's look at this graph here. And just by inspection, if a surveillance algorithm had to find all three red vertices, how much privacy would it have to compromise? So this graph is small enough that we can see that the least privacy cost to finding all the red vertices is just by eavesdropping on this edge connecting red vertices and targeting this isolated red vertex. And this would discover all the three red vertices in this graph while only paying a privacy cost of 2. And no algorithm on this graph can do better than that. So no algorithm on this graph can uncover all the red vertices with a price less than 2, with a privacy cost less than 2. So if we generalize this concept, so we put this into an optimization problem for bigger graphs, and the problem output this very intuitive nature of like, what is the optimal privacy cost? And it turns out that the optimal privacy cost is when the surveillance operations are exactly first eavesdropping on all the red to red edges in this graph, and then targeting any isolated red vertices. And this is because the eavesdropping operation is essentially free in terms of privacy. So when there's an eavesdropping operation between two red vertices, no green vertices are being surveilled, and that's a free operation in terms of privacy. So the only privacy cost comes from the neighbors of the isolated red vertices like this one here. So then the privacy cost can be low bounded by the sum of the neighborhoods of all the isolated red vertices. And this tilde here just means that we don't want to double count any green vertices. So if the same green vertex is in the neighborhood of 2 isolated red vertices, you only want to count it once. So that's the privacy cost. So that's the lower bound on the privacy cost for any surveillance algorithm on a graph. And this is all great because so far it's all been theoretical, but we don't really know the green and red attributes of any graph. And this is just true. So what we were thinking about how to get a sense of what these costs might be on a graph. And so we decided to run a few experiments. And what we did in these experiments is essentially we picked up a real world network and we tried to judge what privacy costs might be in these networks. And here's how we went about doing it. So we used the Facebook ego graph with 4,000 vertices and 80,000 edges. So it's a smallish graph, it's not a huge graph. And what we did was we fixed a number of red vertices in this graph and we placed them at random inside this graph and calculated the minimum or the optimal privacy cost. And then we repeated this for about 500 runs. And each time we placed the group of red vertices somewhere else at random, and we averaged. And this is just to get a sense of what the privacy cost would look like in a real social network, so to speak. So here's like a plot, and we had 500 runs for each of these numbers of red vertices. So we started with 4 red vertices, which is about 1,000th of the network, and all the way up to 500 or so, which is about an eighth of the network. And you can see here that the costs are somewhat varied depending on which vertices you pick up. So, and sometimes you have really expensive runs and sometimes you have not so expensive runs. So we have roughly an average of these costs, which we'll be talking about. And then we also have the scaled version of this cost. So like how much does it cost per red vertex? So you might have a total cost for 4 vertices and you have a different total cost for 500 vertices, but how much does it cost per red vertex in terms of privacy? And here's what the numbers sort of look like. So for 4 vertices, we ended up compromising about 160 green ones. And what does this mean? This is a minimum. So any algorithm would have to compromise at least that much. And as we go down this, we can sort of see that the number increases and then decreases, which looks kind of mysterious. But if you look at the scaled rates, what this means is that per red vertex in the 4 vertex case, we ended up compromising the privacy about 40 green ones. And as this group of red vertices becomes bigger, this cost or this ratio starts decreasing. And the reason for that is because this graph is fairly well connected. So what happens is that once you place about 500 red nodes at random in this graph, they're all very likely going to be connected to each other. So it's very easy to find the red nodes using eavesdropping operations. However, what we think this experiment shows is very interesting because in a real world network, presumably you're looking for a small, like a few hundreds of people inside millions of people. So if you were to extrapolate the results, we would expect, and we think it's very interesting to sort of run experiments on bigger graphs, and we plan to run more experiments on bigger graphs, and we would expect that this cost would skew much more severely. And we would see a quite almost unacceptable privacy cost per green vertex in true social networks and realistic social networks. So that's just an interesting experiment, and there's many different ways of setting this up. You can think of different applications and different ways of placing the red vertices in this graph, and we think it's interesting to study these costs in a social network. So that was sort of the first set of things I wanted to talk about. This was surveillance and privacy. I talked about our framework, the graph VE chi, with vertices V, edges E, and the coloring function chi. The two operations that we allow on the graph, eavesdropping and targeting, and the minimum privacy cost, or the optimal case, or the privacy cost, which is determined by the neighborhoods of the isolated red vertices. Now I want to change tacks a little bit and talk about social control. And the reason we thought about social control is that surveillance is often portrayed as a violation of privacy. So the main counter argument to surveillance is, or one of the large counter arguments to surveillance is that it violates individuals' privacy. And in fact, even the first half of my talk has been about how surveillance violates individuals' privacy. However, the end goal of surveillance is control. So surveillance is a tool of control. And what kind of control? The government wants to control society, and what could that possibly be? So we define a state of social control. And what is a state of social control? It's a state in which the choices of an entire society are dictated by the government in power. So in order to talk about the choices of society and what individuals end up doing, we formulate a game or a surveillance game, and we talk about a strategic interaction between the government and the people in society. So on one side, we have the government, and on the other side, we have individuals in society. And each individual has a set of choices. Again, let's say there are only 3 choices just for the purposes of illustration. And the government has a mandated choice, or a choice that the government would prefer that everybody took. And let's say that choice is yellow in this particular setting. And the government uses surveillance as a strategic tool. And what we have to note is that a government is a very powerful entity. So it has a lot of other powers. So it supplements this power of surveillance with other powers such as punishment, the power of punishment. And on the other side, we have individuals, each of whom has a preferred choice in this choice set, which is denoted as CI. And the utility of any choice, or what the individual stands to gain by making that choice, is denoted as UI of C. And the expected utility of the choice is denoted as EI of C, which is the utility over the randomness of this game, which I'll shortly define. And we assume that individuals are utility maximizing. And you might have your objections to this assumption, but for the purposes of this analysis, we assume that individuals always make choices that maximize what they get out of it. So it maximizes their utility. And so that leads us to sort of define this game between the government and individuals. So like this, on one side is one individual, and on the other side, it's the government. And the government has this strategy S, which includes surveillance and possibly punishment. And the individual has choices, and each of these choices gives them some expected utility. And this is the normal or the layout of this game. And so what we show is that there exists at least one strategy under which a government can attain social control. And sorry, before I talk about that, I should also define social control formally now that we know this. So what is social control formally? Every individual maximizes their utility by choosing C star. So regardless of their initial choices and regardless of their initial preferences in this set, if the best response to the government strategy is to choose C star, then we define such a state as social control. And what we show next is a strategy for social control, which is fairly simple. So consider this strategy for a government, sample individuals from among the set of individuals to form a target group T, and use targeted surveillance on every individual in this target group. And what does targeted surveillance reveal? It reveals a lot of data about this individual, and additionally, it reveals the choices that an individual makes. So if any of these individuals are making a choice that is not the government mandated choice, punish them, some P. And this is something that's possible if a government has this arbitrary mass surveillance capacity, as well as the capacity to punish an individual. And what we show is that under this strategy, we show that if the target group and the punishment satisfy this condition, which we call the social control condition, then social control is achieved on the government side. And if we look a little bit carefully at this expression, we can see the somewhat intuitive fact that as the punishment starts getting larger and larger, this fraction inside the log gets very close to 1. And so this whole right-hand side tends to 0. And pretty much for any group size, the government can achieve social control. And that is just the mathematical formulation of what is very intuitive to us, is that if the government could pick somebody at random and punish them a huge punishment, then most of us would not make the choice that the government doesn't want us to make. So, and what we show is that all that was needed for this to happen is the power sort of arbitrary mass surveillance. So the power to surveil an individual at any point of time. And we think that's a very concerning consequence to come out of a fairly simple analysis. So I won't get into the proof right now, but I just want to conclude with some future questions that we think might be interesting for future work. And I talked about our framework. I talked about privacy costs and social control in our framework. And I want to wrap up with some future work. And we think there's a lot of questions that could be asked in this framework, and it's a very interesting set of things to ask. And some of them I'll just pose for this audience if any of you would like to think about them. So the first question is, how do we model auxiliary information about this graph? So all through this talk, I've been assuming that a surveillance algorithm or the government doesn't have access to anything other than the structure of the graph, which is not true. In a realistic setting, a government has access to information about its citizens and individuals in society. It possibly has prior distributions. It possibly knows something about where red vertices might be in this graph. And what happens when that is added into the model? How does that affect the cost of privacy? How does that affect surveillance on this graph? How do anonymous networks affect this model? Again, so far I've been assuming that all the edges in this graph are visible, and the only choice for the government is to whether to eavesdrop on an edge or not. But what if interactions between individuals were not even visible? What if individuals used traffic hiding solutions or anonymous networks? How does that affect privacy, and how does that change surveillance, or how does that affect the kinds of surveillance that a government uses? And lastly, sort of briefly alluded to this, that a government would have multiple costs in surveillance. So there is the surveillance cost as well as the privacy cost. And different governments have different utility functions, so to speak, over these costs. So we can assume safely that almost every government doesn't want to spend, like, not have a high surveillance cost, but different governments would value the cost of privacy differently. And this might be cultural, some of this might be governmental, but when a government has a different utility on privacy of its individuals, how does that affect surveillance, and how does that affect what kinds of surveillance happen in society? And these are just a few of the questions that we think are very interesting. With that, I'll stop. Thank you all for your attention. If you have any questions about this in the next few days, please feel free to write to me. My email address is on the slide. Thank you.
I'm the designated clapper.
Thank you.
Yeah, so if you have any questions, drop them in the Q&A, or even if you put them in the chat, I'll probably see them. And until people do that, sorry, I'm just pulling up the Q&A window so they can see it if people do ask questions. I wanted to ask you about, so I wanted to ask you, I guess it's sort of a pair of questions, which is about the sort of the operations that the government can do when it's in this when it's trying to discover the red vertices, and whether there are like non-trivial algorithms for finding red vertices in terms of privacy cost. So.
Right. So you mean like not sampling algorithms? So
well, yeah. So there's one algorithm which is just sample maybe random vertices or random edges, depending maybe on the connectivity or something.
Right.
Is there anything beyond sampling that you can do with the two operations you have?
So far, probably not. So far, we've not made any assumptions on the graph, and we've not made any assumptions on the structure of the networks. But
Okay.
if we added in some assumptions, so like a little bit of structure. So for instance, if we assume that some of the red vertices tend to be clumped together, right? So that's just a simple sort of assumption. So let's say that, take it in an extreme sense, so let's say that all the red vertices are a clique.
Okay.
Suppose. So then maybe you have something else to do. Maybe you could like run some other algorithm on this graph structure first before you went ahead and tried surveillance operations. Does that make sense?
Yeah, that makes sense. And I guess it's a related question is, are there other sorts of operations that you've considered besides the target, besides the vertex and the edge operation?
So not immediately, but we also considered sort of eavesdropping. So the way we've defined it now, eavesdropping doesn't reveal, like it reveals contingent colors, but these operations could also be probabilistic in some sense. They need not always give you the truth. Does that make sense? So like you could imagine that some like the efficiency, I think, of the operation. Like maybe it gives you the truth, maybe it gives you the true colors, and sometimes it doesn't. Like it's some sort of noisy operation, which I think maybe makes more sense even in a realistic sense. And that is probably something to consider.
Cool. So we have one question in the Q&A. I don't know if you can see it, so I'll just read it. Does that sound good?
Yeah.
The question is, what are the takeaways of your simulation and results for the privacy debate, would you say? So what do you think your experiments have to say about the privacy debate?
Okay, so this would be a little bit outside of my expertise, but I think I would say something similar to what I said after the experimental slide. So I think we have to sort of run more, like understand the true privacy costs. And it seems as though as the networks get bigger and these groups of red nodes get smaller, the cost would be pretty drastic. And what this helps to do is kind of quantify that cost and ask the question is, are we willing to pay that cost? And it's not it's not any longer like a vague, oh, it's compromising a lot of privacy, but we can now say that we have this bunch of simulations and we know that this compromises a lot of privacy and we're not willing to pay this cost. So potentially we could inform some aspect of this debate in that direction, or at least that's what we hope.
Got it. Somebody else asks in the chat, how might your model differ when thinking about modeling government surveillance versus surveillance by companies?
So that's a very interesting question. So surveillance by companies, if I were to hazard a guess, would be, if I were to think about generalizing sort of inside the same framework, it would be to sort of classify these vertices into different like demographics, or let's say for advertising purposes, they want to classify you into people who are interested in some product versus people who are not interested in some product potentially. And I'm guessing this is sort of the way I would frame it. And I think when it comes to corporations, there's this auxiliary information becomes very prominent because there's a lot more information, I would think, that goes especially into like your social media accounts, and big tech, I would think, has a lot more information about an individual. And I think that would have to be considered a little bit more carefully. And potentially they have even more power than the government in terms of knowing information. And like we've heard a lot of talks in this workshop already around this issue. But yeah, that's what I would think.
And about the social control, I wanted to ask about, are there like one thing I sort of thinking about regimes where there's a lot of government social control, there's like people who are on the side of the government, like people who are, you know, snitching on their you know, office mate and telling the, you know, Peace and Reconciliation Commission about what their coworkers are saying. So one question I had was like whether there was like, you could consider a setting where the government could like act on a vertex in a way that like infects it and has that vertex sort of acts on the graph in its own way.
Actually, and that's a very interesting question because there's also a lot of work, like we were reading a bunch of work, and there's also a lot of work in how information spreads through networks. And that's like, how do you optimally disseminate information inside a network? Or how do you, so to speak, set an example? How might the government optimally set an example, and how does that sort of play out? Or even another aspect of what you asked is sort of, how do the choices of the people around us affect us in society? So the snitching thing is one sort of active peer pressuring, but there's also like subtle pressure. So what if all the vertices surrounding you were already making the government mandated choice, and you lived in a society where it's not acceptable? And it's very likely that very soon you would start changing your choices to fit
I
it.
see. So like some combination of government coercion plus like polarization and network effects. Like,
Right. Yeah.
okay.
I think that would also be a very interesting way. I mean, what we have now is just a very simple model, but I think it has a lot of applications.
So there's a couple more questions that came in the chat.
Mm-hmm.
Sorry, I'm plugging my charger. So Jayshree asked, what are your thoughts on a similar analysis? It takes into account the privacy costs, not only for the good actors, but also for the bad actors, and the impact on actors that are typically mislabeled.
Okay, so that's a good question. And so far, again, I've simplified the analysis greatly by assuming that we know who the good ones are and who the bad ones are. And this might not be the right way to think about it, especially when there is a possibility of mislabeling. And so mislabeling, if you notice that we had a notion of correctness, which said that the surveillance algorithm must always output all the red vertices. So there's also a corresponding notion of a false positive. So like you shouldn't, ideally a surveillance algorithm shouldn't be mislabeling nodes, but that's assuming that we know a ground truth. And this is sort of getting into a more philosophical question of what really is bad and good. And that part I'm not sure how to answer, but what we could do is potentially have this notion of false positives and what happens when your algorithm tends to throw up false positives. And that could be something else to look at.
I think we have time for a last question, and then maybe we'll switch gears. So, can the red vertices improve their chances of avoiding detection in these attacks by carefully controlling which other vertices they have edges to?
That's also very interesting, actually. So potentially, yes. And this is if, so say, and this is like one of those adaptive things, right? Like we saw earlier in the clothing forensics thing. Like if you know the government is using blue jeans to track people down, potentially everyone's going to switch to wearing black jeans. So if you know that the government is eavesdropping on edges to find out, then potentially you limit your social contacts and you don't talk to anybody. And that's a very interesting aspect of sort of like, then you'll have to model it more as a dynamic system where like there are responses and then the government changes their surveillance strategy based on those responses. And then this goes on forever in a game of cat and mouse. But for now, we've only considered like the static case. And the algorithms so far, we haven't like made like proposed any algorithms except for like the very naive ones that I was talking about briefly. Um, so yeah, it's an interesting question as to what would happen if these red nodes were adversarial and there were like adversarial structures inside this graph. But maybe if you altered your surroundings too much, that would become an indication somehow of a red node. So potentially the structure of like the graph around you. So you tend to be a person. So everyone else has 50 friends, but you have only 2 friends. Then maybe that's an indication of me what it might be.